Alright guys, I'm going to do a quick series on oscillators because of popular demand. So let's go ahead and start writing some things. First a title, I guess. Ooh. So oscillators and simple harmonic motion is what we're going to talk about. Let's talk about the definition of simple harmonic motion. SHM for simple harmonic motion. Okay. So there are two classic cases that you get for simple harmonic motion. So, and one is a mass on a spring. So you'll have a block here, and imagine this table is frictionless. Everything's frictionless for this because we're living in a perfect world. It's a spherical chicken in a vacuum. Okay, so when you pull this guy to the right, if I give it I'm going to do a position in black. If I give this guy a positive displacement, I'm going to do my forces are going to be in red, then I'm going to get a force that opposes it, right? From the spring. So this tells me that they are in opposite directions. And we could say, instead of force, we could say acceleration if we want to. But this is also a spring, right? So for a spring, I know that force is equal to minus kx. So that tells me force is proportional to x as well. So the definition we want is to combine these things, and really I just need to pull this minus sign over to here. And so the definition of simple harmonic motion that we want to use is going to be that force, or acceleration, I'll write both, is proportional to minus x. So while force is equal to minus kx, acceleration will be equal to minus k over m times x, right? So on the other side, and these are going to be definition of SHM. So the other classic example we have is pendulums. Pendula, if you want to pluralize it. So you have a roof or something you're hanging it from, and you've got your string and a mass, right? So this is your equilibrium position where it hangs just normally. And with the mass over here, just the natural length of the spring when you're not pulling it is the equilibrium position. So if I pull this guy to here and let it swing, it's just going to swing back and forth. And once again, assuming no friction, it is going to swing back and forth forever between those same 2 points. So from here to here, right? And back and forth. So let's consider the forces on this guy. Well, when I've displaced it over here, my forces will be tension and weight, correct? Because the only, gravity and the rope are the only things interacting with it. So if I look at my free body diagram for that, if I drew these correctly, which I don't think I really did, then it's supposed to look kind of like if I take this guy and pick it up and put it there. Actually, maybe I did. So my weight can move over there. So So my net force is going to point towards the center here. So now, I guess that's another part of the simple harmonic motion that we should have, that the force is always pointing towards the center, but that's, I mean, it's implied by the negative sign over here. But it's something I know they specifically ask about in at least one question on your homework. Yeah. So, but you see that if I displace it, so it's going, displace it to the left, my force ends up being to the right. So one thing they actually usually can talk about with this is they just talk about the x component to keep the math a little simpler. And we can do the same things that way, and it's going to end up being actually this exact same thing. We're still going to see force is proportional to negative x, and acceleration is also proportional to negative x from this too. Now there's a slightly different version of the mass and spring, and that's the vertical spring. So if I took a mass and a spring, hung it like that, well, it's going to stretch down from where it would be if you didn't put the mass, but we can still say its equilibrium position is right here. So if I just pull this guy down and stretch it downward, it's going to go up. If I push it upwards, it's going to go down, right? So we're still actually going to get the same result back, which is just going to be it's going to be the exact same thing as up above here, but the only difference really is going to be that your equilibrium position is different than before. So I've got a simulation I can post of that if that helps you out, but hopefully this one is a little bit helpful in definitions for you. All right, I'll see you in the next one.